Welcome to Spring LIB.
Here we have to apply the conservation of energy to the motion before and after the collision. Then we have to apply the conservation of linear momentum to the collision. So after collision, the system moves as a simple pendulum. So if the maximum angular displacement is small, if angular displacement is small, then the frequency we can write it as F is equals to 1 upon 2 pi root of G upon L. This is only when the angular displacement is small. So in the motion, before and after collision, there is energy conservation between gravitational potential energy, that is mgh, where h is the height above the lowest point in the motion, and the kinetic energy, that is half mv square. So there is a conservation there. Therefore, the energy conservation during the downward swing, energy conservation during the downward swing can be written as m2gh0 equal to half m2v square. So from here, we can get the value for v. v equal to root of 2gh0, which is equals to root of 2 into 9.8 meter per second square into 0.100 meter, which is equals to 1.40 meter per second. Now the momentum conservation is there during collision. There is momentum conservation during collision. Therefore, the equation that we can write is m2v equal to m2 plus m3 into capital V. Therefore, capital V can be written as m2v upon m2 plus m3. So putting all the values, 2.00 kg into 1.40 meter per second square upon 2 plus 3, that is 5 kgs. So the capital V would be 0.560 meter per second. That is capital V. Now, there is energy conservation during the upward swing. So that is equal to capital M GH1 equal to half M capital V square. Sorry, okay. So H1 equal to V square upon 2G. That is 0.560 the whole square upon 2 into 9.8, which is equals to 1.60 centimeter. Now, we can calculate the maximum angular displacement, and it is calculated by the formula cos theta equal to 48.4 upon 50 centimeter, which gives you theta equal to cos inverse of 48.4 upon 50, Therefore, theta equal to 14.5 degree. And by using this formula itself, because we have very small angular displacement, therefore, we have the formula for F. We have already written it 1 upon 2 pi root of G upon L. That is 1 upon 2 pi root of 9.80 meter per second square upon 0.500 meter, which is equals to 0.705 hertz. So this is the frequency and this is our angular displacement. So if we have to draw it, it will be like this. This is the theta. It is 50 minus 1.6 centimeter. That is equals to 48.4 centimeter. And this is H1, that is equals to 1.60 centimeter.